I'm very happy to be here. Today we heard it's a formidable crowd today, so I'm humbled to be speaking to you today. Manfred showed something very similar earlier today, not very long ago. We have on the left what we most agree is kind of a grower's dream. We want loose clusters, open clusters, small berries on these clusters, and the berries should all be uniformly ripe at harvest. That's kind of what we would like. We definitely don't want the cluster on the right that's compact, dense, big berries pushing up against each other, and if possible, they're not even uniformly ripe. We agree on that, right? The reality, of course, in the vineyard is often like this. There's large variation, spatial variation, temporal variation. There's variation not just between vineyards, but within individual vineyards. There's variation within the same vineyard from year to year. And that makes our life as viticulturists very difficult. So I was very happy this morning listening to the breeders' presentations, which I normally don't do much or not enough. And they think much more in the evolutionary terms than we do as viticulturists. And maybe we should have a bit of a resetting of our mindset and thinking, what does the grape want to do? Because sometimes that can be in conflict with what we as viticulturists or as winemakers want to do. So here's the job description of a grape berry. How many of you, do you have any winemakers in the audience? Can you do this if you're a winemaker? Good, we have a few. I have bad news for you too, because grape berries really do not care about you at all. I'm very sorry for that. They care only about dispersing their seeds. They have to get their genes out to the next generation. So they have to advertise when the seeds are ready, and advertisement is production of color, production of flavor, aroma components. And then they have to pay a ticket price to ride on the wing of the birds or in the stomach of a mammal, of me. And that ticket price is sugar. You have to pay for that. And that's the only reason that grape berries accumulate aroma, flavor components, nice color, and that they do accumulate sugar and decrease their acidity. That's when the seeds are ready. So here is a term that I hear a lot. We heard the terms technological maturity this morning and other types of maturity. Wine writers and other people often talk about physiological maturity. So I would like to do a quick survey here with the audience if we have time. We have two sets of seeds. I don't know how well you can see these. Who thinks the seeds on the left are more mature than the seeds on the right? Huh. It's not like an election in the US. Who thinks the seeds on the right are more mature than the seeds on the left? What about the rest? All undecided? All right, so looks can be very deceiving, right? These seeds all have the same maturity. They were actually harvested at the same time and the end of the growing season. This is Cabernet Sauvignon, as the slide says. And one of the seed lots is from healthy, mature, fully ripening berries. And the one lot on the right is from a lot of seeds or from berries that have a physiological ripening disorder. And in this case, the berries just stop ripening at about 12 or 14 degrees Brix, which is just during color change. But the seeds are all mature. The seeds are ready to germinate. They have the same weight. They have the same number of seeds in these berries, the exact same germination rate if you do it. So if you want to talk about physiological maturity, that is when the seeds are ready to germinate. So physiological maturity for the berry is veraison. Everything that happens after that is just to help the seeds get dispersed. Let's stop about talking physiological maturity at 22 Brix or 27 Brix or something like that. It has nothing to do with reality. So maturity, just the state in which the fruit is best suited for a particular purpose. And that means different things to different people. It means different things to different winemakers, different things to different consumers. That specific purpose is what determines the maturity as we see it as viticulturists or winemakers. Something else to keep in mind, if we want to just very briefly touch on some ripening processes. I don't have very much time to touch on today, so I want to go on to environmental variables that change ripening. But most of the changes that occur during ripening happen very early on, while a cluster is changing color. If you look at these clusters down here, I don't know how well you can see this dot, but here we have a cluster that's just starting to change color. And even this cluster here can have berries that vary from 6 or 7 degrees Brix to 20 degrees Brix on the same cluster. So we decided that in terms of sampling, it doesn't make much sense to say we sample at veraison. What is veraison in this case? So we now sample berries when we do maturity studies based on visual color. And I could show you correlations. They correlate very well with berry weight, with Brix, with acidity. Here are just a few examples on the left where we sample berries. We now split this into green hard and green soft because, as we heard this morning, berries start to soften and then accumulate sugar, and then they go and change color. So then you have pink, purple, red, whatever, and then they go blue. And then you cannot see the change anymore. But during that color change of an individual berry, the Brix level can go from less than 8 to more than 18. That can happen within a few days. The acidity drops from 25 or higher grams per liter to maybe 10 or less, depending on the genotype, on the variety. The pH increases dramatically just during that color change phase. And then the change slows down. You have more changes as the berry progresses, what we call ripe. We just call this arbitrarily ripe from about 20 to 24 Brix, and then overripe above 24 Brix. The physiological maximum that a berry can accumulate sugar to, this is not physiological maturity, but the physiological sugar maximum is about 23 to 25 Brix, depending on the variety. Any additional gain, and I come from the west coast of the US now, where it's very common to have 15–16% alcohol in the wine, so we harvest at 26 to 29 Brix or higher. That gain is all due to shrinkage of the berries, so the berries lose weight. They do not accumulate sugar anymore this late in the growing season. So I want to go back just briefly to berry size. We spend a lot of time talking about berry size, and I know winemakers, we said it earlier, like small berries because they have a higher skin to juice ratio and so on. And here are the variables that eventually determine berry size. Size is essentially determined by the amount of water in the berry, 70 to 80% water at harvest, depending on the Brix level and sugar level. So this balance of water between water coming into the berry and water leaving the berry is what determines the final size. And that final size is restricted by the extent to which the skin can expand during ripening. So during veraison, we have an increase in phloem influx. The berries are starting to accumulate sugar. We have a decrease in xylem influx. We have a change in transpiration from the berry. The berry loses water by transpiration. And we may also have water that flows back from the berry to the shoot or to the roots, xylem backflow. And all these different flows eventually determine the size of the berry. This just little point here, because the phloem inflow increases so strongly, the berries become very strong sinks at veraison. The berry becomes relatively insensitive to changes in soil water at that point. Very sensitive before veraison, very insensitive later. So a word on transpiration. We just published a paper about a year ago on berry transpiration, and some of this is information that Stefano Poni, sitting up here, published 20 years ago, and we find, oh, similar results, surprising. So transpiration in berries is mostly through the cuticle. Their stomata are occluded by wax and suberin by veraison, so post-veraison during ripening, there's no stomatal transpiration. That means berries are essentially designed to minimize transpiration or water loss. And yet transpiration helps with ripening because vapor pressure deficit, the temperature, humidity of the air drive how much water the berry evaporates. If water cannot evaporate from the berry cannot release the phloem pressure when it unloads sugar in the berry. Okay? When the phloem pressure is not released, sugar accumulation rate decreases. The sugar unloading decreases. And when sugar accumulation decreases, and you can see this in the picture over here, where we inhibited transpiration on the Syrah cluster, no inhibition here, sugar accumulation rate decreases, so does color accumulation, because sugar is a prerequisite for color accumulation or color change. So rapid ripening is driven by in a part driven by rapid transpiration rates. That means if you're in very humid conditions or cool conditions, this is one major reason that the ripening rate is much slower than if you're in warm and dry conditions of ripening. So one of these potential spoilers of grape ripening is cool, humid conditions. And then something else about berry size is we've discovered that berry size is actually determined very early. Here are two different experiments on the left. My eyes are not good enough to see this red dot. But on the left-hand side, that's a Cabernet Sauvignon experiment, and then in the middle is a Sauvignon Blanc experiment. Here we manipulated, on the left, we manipulated the bud temperature and the temperature of the shoots as they were just emerging from the buds. And then we measured the size of the flower caps as they were falling off during bloom, and then again we measured berry size, and you can see that the two are correlated. So small flowers, if you have cool conditions early on that lead to less cell division and so on in the flowers, lead to small berries later on in the growing season. Berry size can be determined very early. Warm conditions eventually lead to bigger berries. Similar with water conditions. If you have more water supply before veraison, during the cell expansion phase and cell division phase up to veraison, then the berries will become bigger. Here is correlation on the right between lag phase, pre-veraison berry weight, and harvest berry weight. The harvest berry weight is essentially determined by veraison. There's very little you can do as a viticulturist to manipulate berry weight during ripening. There's more or less a twofold increase in berry size during ripening. And then this is something I hear a lot from some winemakers, but also from wine writers, that we don't know much about irrigation, but the one thing we do know is that the irrigation late in the growing season or rainfall will dilute wine quality. Well, does it really? I mean, so we did the experiment. Up on top is the correlation between stem water potential of the plant, that's a measure of plant water status, as averaged over the pre-veraison period, and then the berry weight at harvest. And of course, we have a correlation. So more water before veraison leads to bigger berries. We did the same correlation with average water status of the plant after veraison and berry weight. Absolutely no correlation at all, so I'm not showing it here. What I'm showing here is the extent of berry shrinkage in 3 different varieties and average plant water status. So what we found was that berry size can be increased or decreased depending on water status, more water, bigger berries, less water, smaller berries, before veraison. Berry shrinkage during ripening late in the growing season can be decreased by water status as well, but not berry growth during ripening. And on average, I wrote it here, we gain about 1 degree Brix on average for every 5% weight loss. So if you tell your grower, if you're a winery and you buy fruit, you tell your grower, you have to wait for 28, 29 Brix. You also need to negotiate the price because the weight for the grower decreases. The grower is evaporating profit, essentially. But there is some truth to this thing about berry size and so on, but the truth is not in how much water you apply to the soil during ripening. I can show you a lot of results where berry size is completely independent of water supply to the soil, but when it rains, then the berry can swell, it can absorb water through the skin. The berry will eventually crack, it can split. And here is an experiment. First of all, the critical pressure that leads to berry cracking decreases exponentially just during that color change phase, as a berry even changes from green hard to green soft before it accumulates more color. And then the berry becomes very susceptible to splitting because the skin becomes stiff, becomes rigid. If a berry does crack, and here we did this experiment on the left, where we were kind of leaching sugar out, and you can see berries that go from 20 degrees Brix to 2 Brix. If the rain continues and washes sugar out, the sugar is now not in the berry anymore, it's on the vineyard floor available for the microbes. So this is where the problem comes in. If you have rainfall close to harvest, you harvest fruit that has cracked berries, but some of the fruit has very low Brix levels because the sugar has been leached out. If it stops raining, those berries will often shrink and the sugar concentration increases again due to concentration effect. More about water deficit. Of course, water deficit has an effect on how much sugar is available for the berries. Here is some work we did where we played with amount or number of shoots, different numbers of shoots per vine, but this is relatively unimportant here. What I'm showing is the relationship between daily maximum stomatal conductance and the amount of carbon that ends up in the fruit. And you can see they're reasonably well correlated because under water deficit, the vines, depending on variety, will respond by closing the stomata. When they close their stomata, they produce less sugar in the leaves. There's less sugar exported to the fruit. Therefore, less sugar accumulation. So if you have less water before veraison, typically the result is smaller berries. If you in turn have less water after veraison, typically the result will be less sugar accumulation and eventually berry shrinkage. And then ultimately you need to do the experiment and take it all the way to the wine. Here's an experiment again with Cabernet Sauvignon that we did over 3 years. And this is a message for all of us viticulturists. Vineyard experiments have to be done over multiple years. We find repeatedly in every experiment that I'm involved in that goes over several years, the vintage variation is always by far the greatest driver of fruit composition. Whatever we do in the vineyard is just small manipulation within a vintage. There's big differences between years, and that was true here. The treatments are not so important. Here we're looking at wine anthocyanins and wine tannins and small and long polymeric pigments and so on. The difference here is that tannin variation in this experiment was driven about equally between vintage variation and irrigation variation, but anthocyanin variation in the wine was completely dependent on the vintage. That means on temperature during ripening mostly. Another take-home message from this, if you have applied too much water, if it has rained too much early in the growing season, you cannot compensate by water stressing late in the growing season. The simple message is dehydration does not make berries more mature. You do not end up with better wine quality if you withhold water later on during ripening. We often talk about water deficit effects being effects of berry size, right? Because of a juice to skin ratio and so on. There may be effects on ABA, abscisic acid production, that will have an effect on sugar and color accumulation. But here is something that we sometimes overlook. With less water in a dry year or with less irrigation, we typically get smaller canopies, shorter shoots, less lateral shoot growth, and smaller canopies are more open canopies. More open canopies means there is more fruit exposure to the sun. When the fruit is exposed to the sun, it gets heated by the sun. You can maybe follow these lines. Here is ambient temperature, the gray line, over about a week's time. And then this is actual berry temperature, about 15 or so degrees Celsius, warmer of exposed berries, but the same temperature as the air temperature when the berries are shaded. So most irrigation effects with fruit exposure and so on, they may not be direct effect on biosynthesis of certain compounds or gene expression or so on, but they may be translations of the water effect on canopy differences that have an effect on berry temperature. Something we should maybe keep in mind a little bit. Exposed berries are warm berries. I've said this already, vintage variation is key. When you look at these graphs, 5 years of data, one cultivar, and yes, we find correlations between sugar and acid degradation, sugar accumulation and acid decrease. We find correlations between the increase in sugar and the increase in color. But look at the shift at the same Brix level. The temperature drives malic acid degradation. The temperature drives anthocyanin accumulation. If it's cooler, you get more anthocyanins and so on. So huge differences, twofold color differences, up to tenfold differences in flavor compounds from vintage to vintage at exactly the same Brix level. Temperature can be limiting. We did this experiment just to play a little bit with fruit. We put potted vines in a cold room overnight for 5 days, and we took them outside in the bright sunlight, ambient conditions during the day. Just decreased night temperatures below 10 degrees Celsius. Sugar accumulation completely stopped during that time. Then it accumulated again when we took the plants out. We put the plants again at lower than 10 degrees Celsius overnight only, just overnight. Sugar accumulation completely stopped again. And then it increased again later on. So temperature drives, sugar accumulation drives sink activity for the most part, but it also drives source activity. Temperatures below about 10 degrees and above 40 degrees Celsius will eventually lead to arrest of sugar accumulation. So since we're talking about temperature, here's a list of compounds that I found to be, this is from a literature review, these compounds are kind of affected by temperature. I don't have time to go through each of these, but you can tell that most of these components are somehow affected by temperature. And this is where some of the difficulty comes in, like I said earlier, exposed fruit or warm fruit. Here is that difference between east and west side of the canopy that we often see in our conditions where we have bright sunlight. We often see the berries starting to ripen on the east side of the canopy, and they're still green on the west side. They have too much sun, they're too warm, they're just waiting for the temperature to cool down. So you have that exposure effect that affects both temperature and light of the berries. The two are inseparable, like twins. And these components are all affected by light. Again, I'm not going to go through the list. You can see that some components are directly affected by visible light. Others are more responsive to ultraviolet, UV light. Some are responsive to UVA, others more to UVB. Different components respond differently to the spectrum differences of light. So is more sun exposure always better? We hear a lot here, and I hear it all the time when I go to conferences. You have to remove leaves in the fruit zone. When a winemaker walks into a vineyard, if they do get out of the car, I'm sorry, winemakers, I usually make a little bit of fun of you. But, the winemakers walk into a vineyard and typically they say, oh, too many leaves or too much crop, so you have to remove leaves. Right? You're exposing the berries more. Is there something like too much sometimes? This is work we did in collaboration with Osvaldo Faila's lab, where we looked at Riesling and Chardonnay. It was an irrigation experiment, and we were interested in, does irrigation have an effect on components in the wine that would lead to astringency or bitterness? And of course, you don't want any astringency or bitterness in a Riesling, whereas in a Chardonnay, you can get away with some astringency, some mouthfeel, right? We found we varied water supply by 50% and more. We found absolutely no direct effect of irrigation. The effect was all because of this light exposure from smaller canopies with less irrigation, just like I said before. With more exposed fruit, we find, what did I write there, 6 to 8 times more flavonols. Flavonols are bitter tasting compounds in white wines. We find 2 to 4 times more flavan-threols, monomers, dimers, trimers, polymers, tannins. 2 to 4 times those are astringent, partly bitter compounds. This is not what you want in a white wine. So we also found more sunburn in the exposed fruit, of course. So yes, there can be something like too much fruit exposure. We have to be careful about that. And that's one thing that we need to be careful about when we do these early defoliation experiments, because grapes acclimate to that early defoliation mainly by producing more flavonols. So think about that when you do white wine grape trials. So I want to switch to nutrients for the rest of my presentation. Because nutrients are also part of the environment. We supply nutrients as growers, nitrogen in particular. Grapes respond to nitrogen by growing more. by producing bigger crop. You can see in this correlation here, more yield, more growth. When I look at this slide, more growth often means more competition. Here is a slide from a Cabernet Sauvignon on the left-hand side. Cabernet Sauvignon experiment. Number of growing shoot tips during ripening versus Brix levels at maturity, or sugar levels. There was competition. The more shoot tips you have that are still actively growing during ripening, the more they will compete and draw sugar away from the fruit. Our goal as viticulturists would be to stop ripening, stop growth completely before ripening begins, so that the vine can focus just on fruit ripening during that phase. Okay. Nitrogen has an additional effect, not just in growth, but it directly affects gene expression of genes that are influential in phenolic metabolism. There's something about the need to assimilate nitrate in the plant and produce proteins, amino acids and proteins that will interfere with gene expression for phenolics. So by decreasing nitrogen supply, we can, as you can see on the right-hand side, we can increase color, we can increase phenolics production, but we have to balance that with other aroma flavor components. Some aroma components require some nitrogen to be at optimal concentration. So maybe instead of just talking about fertilizer supply and so on, we could talk about regulated deficit nutrition, like we talk about regulated deficit irrigation. We want to have a certain level of deficit nutrition, but we need to know what that level is in order to get the maximum quality. Another example with Cabernet Sauvignon. This is a very old experiment I did a very long time ago, where I changed nitrogen supply just during the bloom period. This is almost like a memory effect on the plant. And then I changed light levels. I simulated clouds, different levels of cloud, just during the early ripening phase. And then I measured anthocyanins and lots of other components. Here are the 5 major anthocyanins that you can see. And you can see that there's a gradient from the top left to the bottom right. A lower overall concentration of anthocyanins in the bottom right, and those anthocyanins are dominated by just one compound, that's malvidin-3 glucoside. Right? So not only does the overall concentration of anthocyanins change when environmental conditions change, but the distribution of the individual anthocyanins change as well. There's much more balance in the color profile with high light conditions during ripening, but also with lower nitrogen supply. The worst combination is to put a lot of nitrogen early in the growing season, stimulate shoot growth, and then you start hatching the canopy and decrease leaf area continuously because the vines just will not stop growing. Then you end up with an unbalanced color profile and very poor color. Nitrogen is also important as a component of yeast nutrition. Like I said, yeast cannot live by sugar alone. They need other components, amino acids and so on. This is from an old irrigation experiment done in Australia with a PhD student there. It's not so important what these treatments are. You can guess what PRD might be and RDI and so on. What is important is that red line. As you apply less water, the vine also takes up less nitrogen. So you have to supply relatively more fertilizer to get to the same level of yeast assimilable nitrogen. Vines cannot use proline, which is not very much affected here by these different irrigation and fertilizer treatments, but it has to use arginine, which is very strongly affected. So those are things we have to keep in mind when we design fertilizer plants, for example, for our vines. One more nutrient, and then I will stop talking about nutrients because my time will soon be up anyway. Potassium can be a little bit complicated. We often tend to forget that potassium is a major driver of acidity in juice and in wine. Maybe not of organic acids, but certainly of the pH. We find that the pH of grape juice, therefore of wine, is about equally affected by the variation in titratable acidity, mostly malic and tartaric acid, as it is by potassium in the juice. So variation in perceptible acidity pH is about equally driven by changes in acidity or acids and changes in potassium, because potassium substitutes for hydrogen ions or protons in the juice. So more potassium means higher pH. Late harvest decreases not only acidity, but it also increases the influx of potassium as long as the phloem is still functional, so the pH increases with late harvest. If you remove too much fruit, again, the winemaker comes and says you have to drop 30 or 50% of your fruit to the ground. You remove too much fruit, you have too high a source to sink ratio. There's too much potassium being loaded in the leaves into the phloem. Potassium ends up in the sinks, which are the berries during ripening, and so too much fruit removal or too little crop drives up the pH. That can be beneficial in a really cool climate where we have too low a pH, but it certainly is not beneficial in a warm climate and in a warming world where the pH is often too high already. Potassium is not very responsive to soil pH. Because often if the vine takes up more potassium, it also produces more malic acid. The two kind of balance each other out. And the final word on soil pH versus juice or wine pH. We sometimes find that high pH soils give us lower pH juice. That's because high pH soils are typically dominated by calcium, and calcium competes with uptake by the roots with potassium. So more calcium in the soil, higher pH soil means less potassium uptake, that means lower pH. All right, and this is the end. Since I have you captive here, I wanted to say that what I'm saying, you can read this in the book. The second edition came out a year ago. If you'd rather read it in Chinese, the Chinese version just came out in 2016. Thank you very much.